Now let's run through the this is the basic circuit. So what is the problem with this common source amplifier, the way we biased it? Pardon? Yes. VGS is fixed. Yeah, so this resistive biasing of the gate has problems, in the PMOS case, just like it does in the NMOS case. So again, we need to basically make sure that we use, what did we do to fix this problem in the NMOS case? We use negative feedback, and we are going to do the same thing with PMOS, but the change is that you are going to tell me what we are going to do now. So all right, so the first bias technique was, remember, the PMOS drain current is controlled by the source gate voltage, and like in the NMOS transistor, the current can be measured in either the source or the drain. So not surprisingly, you have the same bias techniques that we used in the NMOS case will apply for the PMOS too, right. So the first thing there was, we had the grounded, in the NMOS case, remember, we had grounded the gate, we varied VGS by keeping the source fixed, vary the gate potential, and the first technique measured the current in the drain, right. So here what do? The source must be connected to the highest potential VDD, all right, and we compare the drain current with a reference current, right, and go and kick the gate voltage in the right direction, so as to make sure that the drain current is the same as the reference current, correct. All right. So I am not going to write out all that long text in words. Now you should be able to tell me, so this is the drain current, we want to compare it with the reference current. So does the reference current go up or go down? Very good. This is I ref, and this node potential X. If ID is greater than I ref, it means, so ID is greater than I ref is equivalent to saying Vx goes up, which means what? Which means the gate potential is too high or too low? The drain current is too high, correct. That means the VSG is too large, but the source is fixed. So it means that the gate potential is too low. So the gate potential must go up. So if Vx goes up, you must increase the gate potential, correct. And so if Vx goes down, G also must go down. Okay. So what should you do now? You connect the gate and the drain just like we did before. All right. And so this is the first way of stabilizing the current bias. So I mean the bias current in the PMOS case, and then we can use the same potential to other PMOS transistors. So this is I ref, this is, if lambda is 0, the current will be the same as I ref. If lambda is not 0, then there will be an error. So, let us say this is Vx and this voltage is the source gate voltage, let us call that Vt plus delta V, alright. So, for what Vx will the current be exactly equal to Iref? Lambda p not equal to 0. When will Id be exactly equal to Ix? Yeah. So, that will be only the two will be exactly the same when the drain potential of the PMOS transistor on the right, that is basically M2, is exactly the same as the drain potential of M1. The drain potential of M1 is Vt plus delta V. So, that basically means that what is the potential of what is the drain potential of M1? That is nothing but VDD minus Vt minus delta V, which is the drain potential of M1, and this must be exactly equal to Vx. Okay. And how do we go and fix what do we do to fix the another problem with this current mirror, this basic current mirror, is that the output resistance, what is the output resistance? R0. So, what do we do to fix this problem? We connect the CCCS and all that stuff, right? Okay. But as you can see, this ID is now pushing current down, right. So, it is actually a current source, whereas the NMOS transistor is pulling current towards ground. So, it is a current sink, alright. So, the fact that you have NMOS and PMOS transistors on the same chip lead to what is called CMOS technology, and the C stands for complementary, right. And the reason why the complementary nature of devices helps a lot is because you can do things with NMOS and PMOS transistors together, which you could not do with a single kind of transistor alone, alright. Okay. So, the next bias stabilization technique is one where, what did we do the second time around? The gate was fixed. In the NMOS case, what did we do? The gate was fixed, we varied the gate source, we measured current in the source and varied the source voltage to go and control the current. So, we will do the same thing here. The gate potential is fixed, alright, and the drain is some low potential. So, we need to compare the current in the source with a reference current and kick the source in the right direction. So, what do we do? Very good. So, basically very straightforward. You put a current source like that, and then, so let us call this R1 and R2. So, you monitor the potential of this node X. So, if Iref is greater than ID, Vx will tend to increase, but if Iref is greater than ID, it means that Vx was the source potential was too small in the first place, correct, and therefore, just the act of connecting that Iref in the source as shown here automatically ensures that Vx will move in the right direction so as to keep ID equal to I. Right, we have seen all of this in the NMOS class. It's a repetition, right? But I think it's good to have a repetition. All right, and of course, on an IC, it's straightforward to make a current source. All right. Oh, what comment can you make about if you are working with a discrete circuit and you have discrete components, a current source may not be that easy. What do you do then? Pardon? What did we do in the NMOS case? Okay, you can pull out some more keywords and then form a sentence and throw it at me. Huh? I think you not listen to the question. The question is, if you are making an IC, then current source is okay because it will need a transistor, right? And on an IC, transistors are free. Okay, but if you are working with a discrete board where transistors are expensive, what did we do in the NMOS case? That's what I am saying. Throw all keywords that you have learned: inductor, capacitor, voltage source, current control, current source. Yes, Ralph. You put a large resistor, right? And it's understood that if you put a large resistor, what is the meaning of large resistor? If this has to work well, I mean the suggestion is to put a large resistor. What is the meaning of large? Yes, much larger than Rx must be much larger than 1 over Gm. Okay, and if you still followed the line of thought, that will be only possible if Rx is very large, right? Then the drop across Rx also will become large, and therefore it has to be accompanied by an increased supply voltage, right? And these resistors will also be different. Okay, so as to provide the appropriate gate source voltage. So VDD2 must be much larger than VDD1, and that is the penalty you pay for not having a current source, right. So, in the limit that Rx will tend to infinity, the VDD2 will also tend to infinity, and that is when you get a true current source behavior. But the insensitivity with respect to changes in the supply etc. will all depend on this quantity Gm times Rx. Okay. All right. Then what is the third? What was the third way of stabilizing the bias? Well, we kept the what do we do? Measure the drain, okay, let us do that. Measure the drain, the gate is fixed. So, this is VDD, some R1, some R2. You measure the current in the drain and vary the source. So, what would we, so what should I do? Current source in drain, is the current source IRF flowing downwards or upwards? Downwards, very good. Okay, all right, and this is the potential in node X. If X goes up, it means if I call that Y, if X goes up, if X goes up, it means that the drain current ID is greater than Iref. So, the source gate voltage is too much or too little? Too much, correct. So, it should be brought down. So, and vice versa. So, alright. The only way ID will be exactly equal to Iref is when the potential of node X is it is constant, right. So, basically you compare the potential of node X to a constant, some Vref, and use an op amp to go and kick Y in the right direction. Okay. What might be the signs of the op amp? Minus, plus. Okay. Now, to make it a common source amplifier, it is very straightforward. The same old, right. Whatever we did with the NMOS case, you can do with the PMOS case. And the last thing was what? We measured current in the source, okay, the Iref, drain is fixed. What do we do? This is ID, we want to fix the gate potential. So, what do you do? You compare okay, you compare it to the constant and go and kick gate voltage in the right direction. And what must be the signs on the op amp? Plus at Vref, minus at. Okay. So, what if this is ID, what is the potential of that transistor at the gate? What is the potential of the gate? Pardon? What is Vs? V reference, okay. Plus VTP or minus VTP? Why is there confusion? Which is a higher potential? The source or the gate? Source. So, what is minus? Yeah, VTP plus square root of 2 ID over mu P C ox W by L. All right. This is Iref. So, this is Iref. ID is equal to Iref, so that is fine. Okay. Now, question for you. If I add a resistor there Rx, what comment can you make about the current to the transistor? What is the current to the transistor? Iref minus? Very good. So, Iref minus Vref by Rx. Okay. but and the gate will therefore will the current decrease or increase? Here decrease, I hear increase. It will reduce, okay, and the gate potential will still be this formula because we used ID in the formula, not IREF. Does it make sense? All right, and so that covers the biasing of all the PMOS transistors. The next thing is to build the 4 control sources. Again, it's same old, it's nothing new. So let's just finish this and wind up. So the incremental voltage controlled voltage source, that was in the NMOS case. I mean, we went through the whole thought process, so I am not going to go through it again. This is RL, this is VI, and this is GM times VI minus VO. And what should the GM be? Ideally infinite. In practice, it's very large. And what is that very large? GM must be much larger than 1 by RL. And what did we then say? That we identified this as the gate, this is the drain, this is the source, correct? And then we said that one way of realizing it was what we did earlier. This is the incremental circuit, we identified the transistor, this is RL, this is VO, this is VI. But remember that the incremental circuit of the PMOS transistor is the same as that of the NMOS transistor. So, there is no reason to identify that transistor as being only PMOS, I mean only NMOS. It could be, you could think of it as being a PMOS transistor. All right. So, this is the NMOS common drain amplifier. What is this? This is the PMOS common drain amplifier. Okay. And again, you know, whether it's NMOS or PMOS, the GMRL must be much larger than 1. Okay. So, the only detail that changes is how you bias the transistor, right. For example, in this case, again I am not going to cover this for this circuit. So, here is one way, I mean we have already seen how to bias the PMOS transistor. So, for example, this is VDD, this is R1, this is R2, all right. So, how do we do, what do we do with respect to the input capacitor and input source Vi, similarly load. Okay. So, this is an example of a PMOS common drain amplifier. So, this basically, as you can see, there is nothing fundamentally new here, right. Once we understand, once we get used to these circuits, to the PMOS transistor, it's just the same repeat of the NMOS devices. And just like how you cannot make an incremental VCVS with a gain greater than 1 in the NMOS case. What is the reason? It is not a 4-terminal voltage controlled current source, it is a 3-terminal one which constrains the kind of circuits that you can build, and likewise with the PMOS device. Now, and the input impedance, output impedance, gain, etc. are all expressions that we have seen earlier. There is nothing really new. Then it's the voltage control, current source. Again, now I am going to dispense with even drawing the GM. So this is R, this is VI, this is IO. What is IO in terms of VI? Incrementally, if GM tends to infinity, this tends to 1 by R times VI, right. If GM does not tend to infinity, then it is this expression, right. Now, if you want to build this with PMOS transistors, what will you do? I mean, in the incremental circuit, nothing is to be done other than no changing drain and source. It is just changing only the direction of the arrow in the source, right. Remember that the incremental model of the NMOS and the PMOS are exactly the same. So, as far as the incremental circuit is concerned, if you had a device like this in the incremental equivalent, okay, it is exactly going to be the same, assuming the transistor, PMOS transistor is biased properly. Whether you have this or that is immaterial, okay. So, now how are you going to bias the device now? Yeah, pick your favorite scheme. Again, let us this is VDD, this is R2, this is R1. This is VI, let us say this is RL. What is the incremental current going in there? Yeah, it is the same thing. IO is 1 over R times GMR over 1 over GMR. Is that clear? Okay. So, that is the incremental current controlled, voltage controlled current source. And again, the expressions for output impedance, input impedance, gain, etc., are all the same. There is no point in rederiving all of that all over again. The next one is the current controlled voltage source, and again I am going to dispense with all the discussion. In the NMOS case, this is what we had. Okay. This is IS. Then what happens now? What do we do? In the PMOS case, the incremental diagram remains the same. So, all that we need to do is identify, think of this as a PMOS transistor rather than an NMOS one. You bias up your transistor your favorite way. Again, I am going to pick something. Let us say I pick, for a change, I put a large resistor in the source. Okay. So, this is my bias circuit. So, tell me what all I should do to make this look like the circuit on the left for incremental signals. Let us say some resistor R1, R2. Yeah, what should I do? Okay. That is the input source. Okay. Connect gate and drain. Yeah, use a large capacitance in series if you don't want to disturb the operating point. Okay. What else? Okay. That is RL. Okay. What else? We need the source to be incrementally grounded. We connect a capacitor, right? And as you can see, there is pretty much, I mean, any of these circuits you can take, you could have done what we had discussed earlier, namely, you take the NMOS circuit, you replace VDD with minus VDD, replace the NMOS transistor with the PMOS transistor, add VDD to all nodes and flip the circuit upside down. That will give you the same circuit that we have got here, alright. And so, this is the transimpedance amplifier, and as Gm tends to infinity, the transimpedance tends to 1 over R, the input impedance tends to 0, the output impedance tends to 0, alright. So, the last control source is the current controlled current source, which was the common gate amplifier. This is I out, this is IS, and again same old, what do we do? Replace IS, okay, and again bias the transistor properly. For example, like this. So, this is IREF, this is IS, some RL here, and this incremental current is IO, which is the same as IS, and the gate must be grounded. Put the large capacitor here. So, today we have completed, basically we have gone through all that we have done with NMOS transistors. We have repeated action replay with PMOS transistors, okay. So, with this we are now ready to put, we are now in a position, now that we understand that PMOS transistors, how they work, it's just a minor change in the mode of operation, but otherwise fundamentally it is the same set of equations, same similar, in fact the same small signal equivalent, everything is pretty much the same. So, now we should start exploiting the complementary nature of NMOS and PMOS transistors and start to see how we can put these two together to do things that were not possible with a single type of transistor, alright. So, we will start doing that in the next class.